Good morning, developers. If you are new to the channel, my name is Rob, and it is CS Thursday. Thursdays when we look at computer architecture, programming languages, data structures, theory behind our craft. And today I want to look at this question: which one is better, encryption or hashing? And everybody knows what encryption is, or at least has been exposed to it. It's totally unavoidable. Hashing is a different matter. It took me, when I was early on as a developer, to figure out what exactly hashing is. How is this useful? And we'll come to that in a little bit. And then someone explained it to me, and all of a sudden it made a ton of sense. And I'll warn you up front, which one is better? That is absolutely the wrong question to ask. They are totally different. You use them for very different reasons, and I hope that will become clear. The process for both of them, though, so we can kind of start on how they're similar. If we have, say, a string, okay, and both of these can be done on any type of digital asset, pretty much. Text is easy to work with because I can write it, and it's easy to use as an example. We have ABC, and we need to get it into some other format, but we need to be able, but it needs to maintain some kind of connection to the original. So we use a cryptography process, which is to say we take the string ABC, we pass it through some crazy math formula, and out the other side, I'm just going to make something up here, we get $7. Okay, I made that up. But this is the process both go through. The cryptography process, where we take a piece of input, text, we send it through some math formula that we don't understand and we don't want to understand. Maybe you do. I've been doing this long enough. I'm happy to let the mathematicians figure that out as long as they give me a module to work with. I don't want to know how it works. We get something on the other side that is mathematically related to the original text. Okay, that is the basic concept. Now, there's also, as part of this math formula, something else that can be done is when it goes through this process, there might be something where you would where you would add salt, and so you would take ABC and you would add something to it, pass it through the formula, and then what you come out with on the other side is even a little bit trickier. We will come back to that in just a second. Why would you want to do this? Well, the most obvious reason you probably are already well aware of is we have some sensitive data. Whatever it might be, whether it's a password or a credit card number, a social security number, or even just somebody's cookies, a bunch of tracking information. Whatever it is sensitive and it needs to be protected. There are sort of three different states that a piece of data can be in. We can have data in transmission. That means it's being passed from one place to another. So usually on a network. We can also have data at rest, meaning the data is being stored. And then we also have data in use, meaning we are working on it. Now, when we are working on it, right, when we're doing something with the data, generally speaking, that means we need ABC, right? We want the original native thing, whatever it happens to be. But in these other cases, there's lots of reasons, but sensitive data is the easiest to think about. If you've got data at rest, we'll start with that one, okay? So you have a database, and you are going to store a username and a password on there. The password, maybe the username, maybe not, but the password absolutely has to be in some other format. We cannot store ABC on the server. Why? Well, you probably work with other engineers, or there might be other people on your team who have access to the database. They may just decide to go rummaging through and grab usernames and passwords, and I guarantee most people, even this day, still have the same password for their banking website as they do for yours, and they're compromised, and it will absolutely be your fault. It could be that maybe the database is stolen, right? Somehow it's compromised, someone gets a copy of it, and if it's in English or Hindi or Mandarin, whatever format, again, they have instantly compromised with no work a bunch of user accounts, and it will absolutely be your fault. So data at rest means it's stored somewhere. We cannot store this sensitive data in its native form. Instead, we store it as $7. And that means that whoever is going to be looking at it, whether it's encrypted or whether it's hashed, they are going to need to be able to figure out, it's not going to be useful, because what they need is ABC, and what they have is something else. Okay, so that's thing one. There are a couple other cases where maybe we need some kind of digital signature, or we'll say data integrity to guarantee that the thing hasn't been tampered with or whatever. Those would be cases too. Those might be data at rest, but the data in transmission is going to be, we have, let's put over here, this is supposed to be a laptop. I'm sorry, I'm not a better drawer. But we are going to make an HTTP request. We're going to send some data up to the server, or TCP, whatever, it doesn't matter. Something's going up there. We cannot send ABC naked, right, in its native form, because somebody who knows what they're doing can look at the data in the packets, and they see cookies, right? Lots of cookie data with tracking information and all of that. Maybe they see a token that represents their identity, or they see the password in English, or again in Hindi, Mandarin, whatever. This is really bad because you absolutely will be responsible for that. We don't want to pass it this way. We want to pass it this way, our $7. So while it's in transmission, if somebody's watching it or somebody's going to try and look at our stuff, what they'll see isn't useful to them. At least heuristically speaking, it's not going to be crackable. You won't be able to break through this, instead of something that is useful, which is where they want to get to. Okay, so those are our basic use cases. Which one is better, right? Why would you use an encryption over hashing? Okay, this is the pretty simple part here. Encryption is two-way. That means it is reversible. That means that when we go from ABC through the math formula to $7, with encryption, we can go back the other way and end up with ABC. So if this is on the server sitting as $7, it would be like you have a chest. Okay, you put something valuable in there and you lock it. And whether you leave it in your room and come back and unlock it later so you can get back inside, or whether you send it to somebody and they happen to have a key, they can unlock it and get inside. Encryption goes both ways. You have a thing, a piece of text, it goes through the math formula, you get this. Somebody on the other side, or whether maybe it's you later on, you can use that same math formula in reverse and get back to the original thing. That is the very nature of encryption, and that's why encryption is almost always going to be used for this. It's data that needs to be protected, whether it's at rest or whether it's in transmission, but somebody's going to need to be able to look at it down the road, so we have to be able to go backwards. Hashing, on the other hand, is one way only. You cannot unlock a hash. In fact, I would say not only is there no key, there isn't even a lock. When you go from, and I'll draw it back over here, we'll have ABC, and ABC turns into whatever we had, $7N. I guess it's not quite the same thing. You've got this. You can never get back to this, at least practically speaking. Heuristically, it's not possible. There's no key, but there isn't even a lock. So what's the analogy here? How does hashing work? If encryption is like the locking part, lock, unlock, hashing is going to be more like a blender. Okay, you're going to make a smoothie, and you've got a banana, and you've got an orange, and you've got some cherries, and you've got peanut butter, and you've got some protein powder. That sounds tasty to me. You put it in a blender, and you hit run, and you let it run for a certain amount of time, and then you've got a really tasty smoothie that you can drink. There is no way that you can ever get it back to what it was. You can't unblend it so that you're back to a banana and an orange and a cherry and your peanut butter, right, in their original state. That's not possible. It is blended. So how is this ever going to be useful if you can't ever go back? Why would you ever want to do this? That was the problem that I had. Well, if you have a password, passwords are pretty much always hashed. Very, very, very seldom. I can't think of any reason why you would need to encrypt a password other than you're sending it to somebody, like in transmission, you're sending a password up to the server. It needs to be encrypted in that process so that it can be unencrypted when it gets to the other side. But if it's ever going to be stored, like at rest, you would never, ever have a password be encrypted unless you had very, very specific reasons. So how do we actually use it if it's a hash and we can't go backwards? Well, back to the smoothie analogy. If you know the recipe, right? But 1 banana, 1 orange, 6 cherries, a quarter cup of peanut butter, blah, 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 right? Put all of this in the blender, this particular blender, put it on high for this long, and you will end up with exactly the smoothie every time. Then that means you can pass it back through the same formula and end up with the exact same smoothie. Okay? In the case of the math formula with the cryptography, it's way more sophisticated than a blender. If you give me this, okay, I will store this on the server. Next time you come back, if you forgot your password, I can't help you. This is what I have, and that's not going to be useful to either of us. You're just going to have to reset your password. That's how it almost always works. But if you give me this, I'll run it through the blender. And if what I get matches what I saved when you first told me your password, I know you are who you say you are. I know you have the right password. I just cannot go backwards. You give me the same thing, I'll make the same smoothie. If it's exactly the same, if it's an exact match, then this is a legitimate password. That is the nature of how hashing works. So I got the board cleaned up, and I want to do a quick chart here. Which one is better was our original question. That's the wrong question. The question is, which one should you use based on your current use case? And the really fast top level, if you forget everything else, two-way is required, is the easiest way to think about encryption. If somebody else needs to be able to take the thing and reverse it, you have no choice. You use encryption, period. If it can be one way, then hashing is better for two reasons. One, it is more secure, and I'll go ahead and put this up here. It is more secure because there's no key. If there's a key, that means it can be opened by the right person, yes, but it can also be opened by the wrong person. So the very nature of something being reversible makes it less secure. If it can't be reversed, it's inherently more secure. The other reason is because hashes are fixed length. What that means is if you have a 10-character string and you run it through a hashing algorithm, it's going to come out, let's say it comes out to be 60 characters. The algorithm you have is 60 characters. If you use the same algorithm and pass through a 10 million character string, you will still get a 60-character hash. It doesn't make any difference how long the data is. The hash will be the same length no matter what. This is good because it means you can plan for it regardless of how big the thing is. You can plan for it to always be this length, which is going to be very small. If you have a 10 gigabyte file, you run it through a hash, it's going to be the same small length. Now, you won't be able to reproduce the file, so that brings us to our next point. What are other use cases for hash, or what are more specific? If you want to guarantee data integrity, I mentioned this a little bit earlier, but that means, okay, you gave me a 10 gigabyte file. It was uploaded, and I generated a hash. You send me that same file, at least you claim it's the same. I can run it through the hash, and if it comes out exactly the same, that means this has not been tampered with. It's in the exact same format that it originally was. If it comes out different, then something has changed, and so a hash is a way to guarantee that something hasn't been tampered with, changed, whatever. We'd also have a digital signature, which I had up there a little bit ago. If you've got somebody sending data from one place to another, and maybe it's encrypted, you want to guarantee that it came from this particular person. If both sides have the same hash, you can run it through and make sure that the hash that came with the encrypted data is the same. If it is, then it's a way, again, because it's fixed length, and because you don't really care what the data is, it guarantees that this came from who said it came from. It has been digitally signed. Hash tables, if you know what they are, you probably don't even need me to mention it, but those use hash functions as well. For encryption, again, back to the really simple answer is that this is two-way. If you need two-way, then that's going to be your use case. We already talked a little bit about it, but data transmission, anytime data is going from one place to another, is practical at all to encrypt it. It's getting so that you need to. It does create overhead, and as I said, it's not fixed length. It almost always gets longer as the data gets longer. So there is some overhead that goes into it. But if you're passing data from one place to another, it's getting important to always encrypt it. If you have stored data, and I'll put not password. So things that a username, an address, a phone number, stuff that you are going to need to be able to process, you're going to need to be able to reproduce, right? Two-way is required. I'll point at that. You get stored data that's not a password, not something that absolutely should never be reversed. That's going to be a very common use case for storage. Database storage. So if you've got maybe copies of your database or whatever you're reproducing, you want to keep it in a format that's protected. But if you're going to need to be able to use it again, right? Two-way is a requirement. You're going to need to be able to take your database file and run it back through so that it is the original data. You would encrypt your databases wherever they happen to be at. All the stuff on S3, on Azure, Blob, whatever, that stuff should be encrypted so that it's safe in case the wrong person gets a hold of it, but you can still reuse it. And I'll go ahead and put that underneath here, backup / storage. Really, all of these are essentially use cases for when you have to have two-way as a requirement. As a final thought, I had mentioned salt a little bit earlier, and I didn't want to move on without talking about that. Both of these can and do use salt. When we go from that ABC and we convert it through our math formula, right, whatever our cryptography is, and we end up with 1, 2, 3. Typically, we won't just run ABC through the math formula. We'll run ABC and then we will add our own thing, and I'm going to put in here XYZ, and that will end us up on the other side. That means that if somebody happens to get 1, 2, 3, this is what's stored in our database, or this is what's coming across in transmission on the HTTP request or something. Whatever the case is, if they get this, they can't just start trying lots of different algorithms, hashing algorithms, encryption algorithms to see if they get a match or to see if they can unlock it. They need the ABC, and they're also going to need to know what the salt is, because both of them are required to go through here. Now, in the case of a password, you give me your password, which is ABC. That's still what you give me. But before I run it through the math formula, I'm going to add this. And this is how we end up getting to our result. So like I said, you'd have to have both pieces and the right formula to be able to get to the other side, or to be able to unlock it if it happens to be encryption. Salt is very important. There are some algorithms that salt 20 times, 100 times, whatever the case is, start adding stuff. You can even go to where you've got ABC plus XYZ and you hash it. You could take this whole thing and you could hash it. You could take this through the math formula, and then you could end up with, I don't know, we'll say 4, 5, 6. You can go as far as you want. As long as the process is repeatable when it comes to hashing, this will always work. And like with encryption, same way. If you encrypt it and then encrypt the encryption and encrypt the encrypted encryption and so on, you're just going to have lots of blocks to undo. But as long as the process is steady, the more times you do it, the more heuristically impossible it will be to crack. So again, which is better? That's not the right question. It really comes down more to, is two-way a requirement, or can it just be one way? Is it still useful if it's a hash? If the answer is it's still useful as a hash, that's generally going to be the better solution, because it's secure and it's fixed length. But if it has to be two-way, you should be encrypting almost everything that falls under these categories, anything that could potentially be sensitive, because that's just the world we live in. Thank you so much for watching. I'll see you next time on another CS Thursday video.